In this presentation, I'm going to explain the basics of generator differential protection. In a generator, we're interested in protecting the stator windings. So from differential protection basics, we know that we want to look at the current coming into the device and the current coming out of the device that we're protecting. If there's a difference, that means there's a fault internally in the equipment and we want to take it offline by tripping a circuit breaker. So in order for me to measure these currents, I have two current transformers. So in this case, these current transformers, they have the same CT ratios. So CT ratio for current transformer 1 and CT ratio for current transformer 2. So we're interested in measuring I1. So I1 flows through the restraining element R1 and I2 flows through the restraining element R2. The difference current is calculated by taking the absolute value between these two currents. The second current we're interested in calculating is the average restraining current. The average restraining current is the sum of the absolute values of these two divided by 2 for the average. Sometimes average restraining, you'll see it as IR average for average restraining. So the 87 relay is going to measure, or it's going to have these currents flowing through it, and then from these two currents, it's going to determine whether or not this relay should trip a circuit breaker or prevent a circuit breaker from opening. So at the very basic level, once we have the currents I difference and I average restraining, if I difference is greater than average restraining, the relay would operate because the difference current is greater than the average restraining current. However, in practice, due to current transformer errors and the external faults, we need to add something to this relay to accommodate this. So it's called the slope of the relay. So K is the slope of the relay, and we're talking here about percentage differential relays. So in this case here, most electromechanical relays you can get in different slopes for generators, so maybe 10% to 25%. And for modern relays, we can actually program this slope to be whatever value we need. So if this is the slope of my relay, let's say this is 10%, we can see that we're plotting on the y-axis, we're plotting the difference current, and on the x-axis, we're plotting the average restraining current. So basically, we're plotting the slope, which is the rise over the run. So the percent slope then is basically just based off of the difference current and the average responding current. So what we're going to do is we're going to then plot where is this current. If it's normal current, it might plot over in this area, so the relay would block. If it's a fault, the current might plot over in this area, so it would issue a trip. So under normal operating conditions, the relay is continuously monitoring or measuring I average, restraint, and I differential, and then it makes a determination whether or not it should trip or block. So normal load may plot over in this area. So this is just telling me I have a high average restraining current, but I don't have a difference current. If I don't have a difference current, that means current in is equal to current out, and things are normal. So this would be a block. I can also look at the slope of my relay, and I can look at the slope of the current. So in this case here, my slope is 0, so it's well below the 10%. If I have a fault, the fault might have a high slope, so a fault may plot in this direction. So in this case here, the slope of the fault is greater than slope of the relay, so the relay is going to trip. So let's have a look at the characteristic diagram of a differential relay just to see where our different kinds of load or faults might plot. So under normal conditions, load would be in this direction. So I'd have no load to up to full load. So essentially we have no difference current, and it's just all average restraining current. But because of CT errors, this current might actually plot over here. So I'm still well below the slope of the relay, so the relay is going to block. If I have an external fault, so an external fault means the fault it's not inside the protective device, it's outside of the protective device. So in this example here, maybe I have a fault just outside of my zone of protection. So this is going to cause a high current to flow. So this current, it's still current in is still equal to current out. However, the current is now a lot higher. So this current here now, this would be considered my external faults. So this current is a much higher value, but due to errors, it could plot up in this direction. So due to CT saturation and other errors, it might plot over here. So under this condition, the relay is still blocking because it is below the slope. And this is a condition that we want. We do not want the relay, differential relay, to operate for external faults. We only want it to operate for internal faults. Now, if I look at an internal fault, it will be in the stator windings. So I might have an internal fault, and this is going to have a high difference current and a high average restraining current. So it might plot over in this direction. So this would be considered an internal fault, and the relay is going to trip. So there's two methods I can use to determine if a differential relay is going to operate. The first method is if we're given the slope of the relay and we're given a load or a fault condition, we can calculate ID and IA average, and then we can plot these on a characteristic diagram. So for example, here's my ID. This direction is going to be my I average. So this is ID, this is IAR. So if we're given the slope, so let's say I'm given the slope for this relay. So this is the relay slope. I can plot I average. So maybe I average plots there. I difference plots here. I can see that the point is below the slope of the relay, so it's going to block. Another method we can use is simply just calculate the fault slope and then compare it to the slope of the relay. So if I know ID and I know IA average, I can simply calculate the slope and then compare it to the slope of the relay to see whether or not it's going to trip or block. So let's do an example to see how we can determine whether or not a relay, differential relay, is going to trip or block. So in this condition here, I have protecting the stator of a generator. So I have CTs on one side of the generator winding, and I have set of CTs on the other side. So these CTs have the same ratio because the generator winding is at the same voltage level. So I have a current of 630 degrees amps on the input and 500 at 0 degrees on the output. So I'm going to have a difference current, but now I want to determine, is this going to trip or is this going to block? So my relay has a slope of 10%. So we want to determine I1 and I2. We want to determine the difference current, the average restraining current. We'll calculate or find the fault slope, and then we'll draw these on a characteristic diagram. So let's have a look at A. So for A, we want to find I1 and I2. So I know I1 is going to be equal to 600 at 30 degrees amps divided by the CT ratio, which in this case is 500 to 5 amps. So we get a current of 6 at 30 degrees amps. I2 is going to be 500 at 0 degrees. Divide this by 500 to 5. They have the same CT ratios. So this gives me a current of 5 at 0 degrees amps. So let's put B up over here. So B, I want to find the difference current. So difference current is equal to, so it's the absolute value of I1 minus I2. And in this case, we have 6 at 30 degrees minus 5 at 0 degrees, and we get 3 amps. C, I want to find the average restraining current. So average restraining current it's the absolute value of I1 plus I2, and this is, we want the average, so we divide by 2, so we get 6 at 30 degrees plus 5 at 0 degrees, and we divide this by 2, and we end up with 5.5 amps. So I have the two currents that I need now, ID and I average restraining, to determine whether or not the relay is going to trip or block. So we could go ahead and draw a characteristic diagram and draw this to scale and plot these two currents, I difference and I average, and compare them against the slope. Or we could, at this point, we could calculate the slope of this fault. So the slope of the fault is equal to I difference over I average. So it's just rise over run. So I difference over I average times 100%. So if I plot this, or if I calculate this, sorry, we have 3 amps over 5.5 amps times 100%. I get a current, percentage of 54.54%. So I can see that since the relay slope is 10% and the fault slope is 54.54%, the relay is going to trip. So basically we're just comparing here that the K of the fault in this case is greater than K of the relay, so we get a trip. Looking at the characteristic diagram for the relay, we could actually plot these points if I drew it to scale. So I could go, I average restraining is 5.5 amps, so that's that point. I difference is 3 amps, which is this point. So I draw this point and I can see that this has a slope of 54.54%, and my relay slope drawn down below here is 10%. So we're well over the slope of the relay, so the relay is going to trip. So just to summarize, when we're looking at calculating whether or not the relay is going to trip or block, we need to just calculate the differential current and the average restraining current. We can either plot the points just like I have on this graph and to scale and determine whether or not it's going to trip or block, or we could just calculate the slope of the fault and compare it to the slope of the relay. If the slope of the fault is greater than the relay slope, it's going to issue a trip. Thank you very much, and that's all for this video.